So we're continuing our dialogue about solving linear and nonlinear inequalities. And in this video, we're going to progress into how do you solve inequalities that are not linear. And this is often where students are less familiar with solving inequalities. So we are going to look at solving quadratic inequalities or even higher order polynomial inequalities. So there are really five main components when it comes to solving polynomial inequalities. When you're given a polynomial inequality, you're going to want to first express that inequality in a form that has 0 isolated on one side. So it's going to look like one of these examples where p of x is representing the polynomial. So 0 is on the other side, all the other terms are on one side, right? And as long as the 0 is on one side and the polynomial is on the other, it doesn't really matter what this looks like, right? We can have less than or greater than, or less than or equal to, or greater than or equal to. We just want to set it up that way. And the reason we do that is because it's easier to relate things to 0, and because we want to be able to solve the corresponding polynomial equation. And most times that we're solving polynomial equations, we are going to want to set it equal to 0 to just begin that. So we're just going to do that. We're going to take that polynomial piece, set it equal to 0, and solve for x. And when we find some real solutions, those are considered to be boundary points. So when you find those boundary points, we move into step 3 and we use them to divide up the real number line. And that's going to divide it into sections. And we're just going to call those intervals. And we know how to name intervals. And if you don't, I'll walk you through it. And then after we have divided up our number line into these intervals, we're going to choose test values in each of those intervals. Okay, and then what we're going to do with those test values, we're going to evaluate p of x for each of them. Okay, and then once we've evaluated it, we're going to see if it satisfies the revised inequality that we wrote in component 1, in step 1. So after we've done that, we can decide which of these intervals will actually satisfy our inequality. So we will use those test values to determine and write the solution interval, and we will make sure we use the appropriate notation. If the inequality is less than or greater than, we will use parentheses, and if the inequality is less than or equal to or greater than or equal to, we will definitely want to use brackets. Okay, so that's the procedure. So let's walk through a couple of examples of solving polynomial inequalities. The first example we're going to look at is a quadratic example. So we're going to solve this inequality, and we are going to make sure we write our final answer as an interval. So this is saying I want all the x's that satisfy this. 2x squared plus x is greater than 15. So remember that our first step is to express the polynomial inequality in a form that has 0 isolated. So we're going to just shift that 15 from the right-hand side to the left-hand side by subtracting it on both sides. And we'll end up with a revised inequality that looks like this. 2x squared plus x minus 15 is greater than 0. All right, so step 1 is done. Step 2, we're going to use that and solve the corresponding polynomial equation. So instead of that greater than symbol, we're going to replace it with an equal sign and then solve this quadratic. Now, you can solve by factoring, you can solve by completing the square, you can solve by using the quadratic formula, whatever method works for you. And I'm going to use factoring here because this one is easily factorable, and this equation will factor into the product of x plus 3 and 2x minus 5 equals 0. Now remember, the whole reason why we set it equal to 0 is to use that zero product property. We want to set each of those factors equal to 0 and solve for x. So we'll say x plus 3 is equal to 0 and 2x minus 5 is equal to 0. And then we will go ahead and solve. And we can solve x to be equal to -3, and another solution is x is equal to 5/2. So we've taken care of step 2. So our boundary points for our number line will be -3 and 5/2. So we're going to use those boundary points to divide up the real number line. We're just going to identify where those are on the number line. We got -3 and 5/2, and then notice that that creates 3 intervals on the number line, right? And here's our 3 intervals: -infinity to -3, -3 to 5/2, and 5/2 to infinity. And notice that we've got parentheses on all the intervals because there is no equal sign on our inequality. Now what we want to do is test these intervals. We're going to select test values in every interval. You're just going to pick a value that is within this interval, okay, and actually within each of them, all right? So you can choose anything you want here. I will always choose something fairly close or easy to evaluate. So I went ahead and chose -5 for this first interval. I will always choose 0 for the interval that contains 0, and I just, for simplicity's sake, since I've got a -5 over here, I chose +5 over here. But again, you can choose anything that's within that interval. Now you're going to use those test values and evaluate p of x for that. So we know p of x is 2x squared plus x minus 15. So we want to sub in 3 separate values. We want to sub in -5 and get the output. We want to sub in 0 and get the output. And then we want to sub in +5 and get the output. And when we do that, we get these values. P of -5 is equal to 30. P of 0 is equal to -15. And P of 5 is equal to 40. What we're going to do with that now is check the output and see if the output will satisfy the revised polynomial inequality. And that revised inequality looks like this. So we want to know if 30 is greater than 0, and it is, right? If -15 is greater than 0, and if 40 is greater than 0. Okay, so we know 30 is greater than 0. We know -15 is not greater than 0. And we know that 40 is greater than 0. So we can go ahead now and identify the intervals that actually work. This one does not work because a test value here does not satisfy the inequality. So we can go ahead and cross those out, and the remaining intervals will be our solution. So it'll be this interval, and this interval will be our final answer here. All right, so what does that mean graphically? Let's take a look. If I'm looking at this graph, the green part here is the graph of 2x squared plus x. And you can see that the dashed line here is the line y is equal to 15. So what we're looking at when we're looking at this graph is what part of the green graph is above the y value of 15. Really look at that. I shaded it so that we could see it a little bit easier. What we want to look at is just focusing on the shaded area. What's the domain of the green? So we're not looking at all at this piece down here, but what's the domain of this green piece? And you can see that that's -infinity to -3. You see that? And then over here, we can see that it picks up at about 2.5, also known as 5/2, and it goes all the way up to infinity. So that's kind of what we're looking at as a graph. And if we were looking at the revised inequality, which I think is even easier to look at, because what we're really doing with that revised inequality is we're saying, okay, what part of this graph is greater than 0 or above the x-axis? And it's easier to see because those x-intercepts show us where it crosses the x-axis. And again, it's everything to the left of -3 and everything to the right of 5/2. Okay, one more example of polynomial inequalities. Here we go. And this one's a little bit of a higher order, but it's not that much more difficult. It's about the same, really. So our very first step then is to write this inequality so that 0 is on one side of the inequality symbol. So we're going to shift that 4x and that 4 to the left. And then we will end up with x cubed plus x squared minus 4x minus 4 is greater than or equal to 0. All right, so now let's take that polynomial equation and set it equal to 0 and solve for x. Now this is a cubic function, but it is factorable by grouping. And you can go ahead and factor by grouping. You'll end up with x plus 2 times x minus 2 times x plus 1 is equal to 0. And when we set each of those pieces equal to 0, we can solve for our solution of this equation. So we would have x is equal to -2, x is equal to +2, and x is equal to -1. So these become our boundary points. And so we're going to go ahead and write those on our number line and divide it up. And notice that when I have 3 boundary points, it separates our graph into 4 areas. Okay, so I've got first area, second area, a little tiny one, third area, and fourth area over here. So those are our intervals that we will end up needing to test. And here they are. Now, what do you notice? It's different this time. When I'm talking about my intervals and I'm naming them, I'm using brackets, and that is because my inequality has an equal sign in it. So I want to make sure that these are bracketed. Of course, the notation around the infinities will still remain parenthetical. All right, so now let's choose some test points. We need to choose 4 test points this time. Anything you want in between -infinity and -2. And just for simplicity's sake, I'm still going to use -5. Between -2 and -1, you're going to have to choose something that's in between there. So there's not an integer in between there. You're going to have to choose a fraction or a decimal to evaluate. Definitely choose something between -1 and 2, and that's where that nice 0 comes in, or anything you want. And then something to the right of 2. And I went ahead and chose 5 there again just because it was easy. Now use your calculator and evaluate p of x for each of those test values. Okay, so p of -5, p of -3/2, p of 0, and p of +5. Okay, and so I did that. So we're going to go ahead and check then and see how those outputs of our test values actually relate to our revised polynomial inequality. So remember, our revised polynomial inequality is this thing. So we want to check and see if our outputs are indeed greater than or equal to 0. So is -84 greater than or equal to 0? Nope. How about 0.875? Well, just barely, but yes, it is. How about -4? That one is not, but 126 is. So I can say that these two are not candidates for our solution, and those then will eliminate these two intervals. So our solution intervals will be these two intervals that remain because those test values, the outputs of our test values actually satisfied that inequality. So we end up with a solution set that looks like this. All right, and so what does that look like graphically? Well, this is a little more tricky, especially the original inequality. I have here in blue the graph of x cubed plus x squared. All right, and with the purple dashed line, and it really should be a solid line if we were really thinking about this as an inequality, we are looking at everything that is greater than 4x plus 4. Now, what we're really looking at is the domain of the parts of the graph that are blue that are within the purple shading. So if you look at that, it's everything between -2 and -1, and we're going to include those endpoints. And then this is not in that shading, but then it goes back into the shading around, well, exactly at 2. And then the rest of the graph will be within the shaded region. Okay, and so that's how we interpret that graphically. Now, if we look at the revised inequality, it's much easier to see because, again, we are relating our inequality now to 0. What part of the graph in blue is above the x-axis, where the y value is greater than 0, right? And so you can see that here between -2 and -1. The graph in blue is above the x-axis. And then again here to the right of 2. So that's what that means graphically. And that's enough for polynomial inequalities in this video. In the next video, we will talk about solving absolute value inequalities. See you there.